From all the way in Lancaster, talking about high-dimensional inference in bioinformatics and genomics.
Thank you.
Oh. Thank you. Can you hear me? Yep. All right, good. I guess you were afraid of pronouncing the my current place, which is Groningen, where I've moved about 2 weeks ago. So still a bit in flux, but it's very nice to give a talk in front of the good and the great, and I'll be trying to show you a bit of a toy idea that I had for a while and try to work on off and on basically in the last couple of months. I'm sorry if there's any imperfections in my talk. I'll blame it on the fact that we had rather a rough weekend. I'm Dutch, my wife is Italian, and we didn't do well. No, I only refer to the football matches, nothing else. So I'll talk a little bit about genomics, which is the area that I'm interested in as application, maybe slightly more than an application. I think it's an interesting field. And the kind of questions it poses are quite large, and it makes you think about model choice, model fitting. It makes you think about very hard about data and all the things. And so therefore I think it's as a kind of an area of statistics which kind of which asks lots of different questions from statisticians, and therefore can be very interesting to look at. Now there's when you talk about systems biology, and the thing that I was asked to talk about, basically you are talking about lots of different things. You can be talking about lots of different types of models as well. There's nothing really that necessarily stands out as being the right model in any kind of sense. I mean, I just wrote down, not completely randomly, a list of things, but they kind of vary from the more abstract way of looking at things, so a larger form of abstraction. When you talk about networks, and we've seen that people have talked about networks in the previous couple of talks, they tend to be talking about adjacency matrices. There's very few adjacency matrices in biology. They don't tend to float around very much. But it's a useful abstraction in many ways. But they're abstraction of things that kind of follow from things down below. I mean, these adjacency matrices, where do they come from? Well, they probably have something to do with the fact that the way molecules tend to interact with one another. And they do interact in rather very specific physical ways. And you can try to model this, and you could choose to model this with differential equations. And Mike mentioned a little while ago that sometimes, you know, if you have data that is actually not single cell data, but data that's observed throughout as a time course in different sets of cells, you can't really be modeling any of the stochastics that is going on inside the cell, because you don't really have time course data. But you could try to model something like an average behavior of a particular cell, and so you would tend to be looking at kind of the ordinary mean average kind of type models, and ODEs is a wonderful candidate for that. But again, you can dig in deeper and say, well, that's not good enough for me. And if you have the data, you could try to look even at spatial analysis of molecules, how the way they move around in cells, including the stochastics, and probably also kind of using the fact where the molecules are actually located in space. So lots of different models, and you can ask yourself what's the right model. And well, you could go a bit further down in history of not really statistics, but there was a dispute in philosophy in the 13th century. One called themselves realists, the other one called themselves nominalists, and one claimed that the world is really as it appears it is, and the other one says that the world is as it appears. And if you think about it very hard, what that means is that realist maybe can be somehow. It's not my cell phone. So, doesn't matter if there's any kind of interesting conversation. Hopefully it will be broadcast on the speaker as well. So the issue there is basically, well, you could think of realists as being our current day scientists, really being butts and knolls about things, knolls and bolts and nuts about things. Basically thinking, well, you know, there's it basically is a form of straightforward chemistry and determinism that makes the world and that makes things go. But that's really not the way we statisticians look at things. We statisticians tend to think about the world in a much more nominalist way, and I would claim that, you know, if we have any kind of forefathers that go beyond statistics, the history of statistics somewhere in the 19th century, somewhere maybe Pearson, if you want to dig somewhere deeper beyond that, you probably would end up maybe near Occam or some people like that as being really one of the earliest statisticians. Because we tend to be rather nominalist about things. We really say, okay, we have a set of data, and it's the data that we want to somehow give some kind of value to, and therefore the right model is the one that it suits the data that we have in some sense. So we try to come up with the right model in such a way that it suits our sampling scheme and suits the model is only as good as if we can actually identify it and estimate it with the availability of what we actually have in front of us. Now, in these kind of complex systems that we're looking at, I'll try to abstract it slightly first in the very beginning before looking at a kind of thing that actually sparked me to look in into these things. I think of the things of what makes kind of system biology very typical is that beyond the data and maybe some parameters, there might be some high-dimensional object. Could be a state parameter, could be just a simply high-dimensional parameter that we are interested in as well. And I think dealing with this type of high-dimensional parameters is what makes system biology kind of a challenging task. We have seen several examples of this, and I'll show you one of this and how it fits into the type of modeling that we do. And the reason why I'm going to look at this is that most of the inference will involve something, calculation of this type, and this can be simply intractable in practice, and therefore are there ways that we can come up with that circumvents this, and many are proposed in the literature, and I'll come up with another proposal. This particular high-dimensional X that I'm going to talk about will be a network as well. And so the way you can think about biological networks in some form of abstraction, so this is one abstraction that I've chosen, which will be suitable for the data that I will have available. If you think about genomics, you don't really have, you know, one-dimensional networks. Networks typically act on quite a few different levels. If you talk about gene expression data, you tend to be over here somewhere. What it means is that basically you have different genes and you measure the amount of RNA from these genes that is being produced in a particular cell. But interactions between genes never really works between RNA. It's only quite rare in quite a rare number of cases in which RNA actually directly interacts with one another. It's typically the way it works via proteins. Proteins are the things that actually, well, RNA is translated into proteins, and it's the proteins that really do things, and it's the proteins that really make interactions work as well. So when you talk about a real network, it typically tends to take place on this scale, although it might actually go that a particular protein interacts with a certain gene by being, for instance, its promoter, rather than having a direct link with the protein itself. But there might be also a direct link with the protein. So the kind of thinking about networks is rather complicated. But I will, for simplicity, focus on indeed just two-dimensional networks. And so I'm going to kind of map the whole thing down and just try to come up with a description of a network of this type. And it's known that in these kind of genomics networks, a couple of properties hold, which have become quite popular in the last, well, about 10, 15 years. The ideas of small worlds, the fact that there may be hubs in these networks, and the idea of centrality and lethality of certain hubs. What it really means is that you all have heard probably the popular story about it, basically that just like the internet, probably there are certain nodes inside a genomic network. These probably are proteins that are very crucial. They activate the expression of lots of other genes, and therefore basically they can be seen as at the center of quite a number of genes. For instance, this one and this one over here. If you want to go from one particular, if you were to want to walk on this open network, you could go from one gene to another gene very quickly by simply passing through a few of these hubs. That's the small world property. And the other thing that these hubs typically have, if you're going to kind of do something with them by somehow knocking them out, you tend to basically destroy the little beast that you're working on. If it's a yeast and you knock out one of these central genes, you basically kill the organism. And that's the centrality and lethality argument of these type of networks. Now, a couple of things these are clearly biological interpretations, to the interpretation about centrality and lethality, but the other two, the fact that there may be hubs, there may be small world properties present, is the things that we could try to model in some kind of sensible description of this particular network. So one way of doing this, or one way of starting to do this, is first of all thinking about our network as an adjacency matrix. So we can think of it, instead of this particular graph, you can think of an adjacency matrix. Our aim of our analysis in this particular talk is to think about trying to infer this particular adjacency matrix from a set of data. In most cases, we like to think of this particular network as being directed, because there's typically quite an important interpretation connected with the directionality of the network, and that's going to be quite important. The data that we have, well, typically most of the experiments, one of the ones that I'm going to describe today, we will have time course transcription data available. They're not as nice as what Mike showed you. They're not just from a single cell in which you measure the transcription of a set of genes across time. These are typically destructively sampled objects, and so the best thing you can do is modeling something like an average behavior over time of a population of cells. But okay, so we have a time course, sets of data, not really a time series, as I said, and that's going to be a type of, they come basically from microdata. N genes, C time points, the drawing is not very good, probably N is going to be very large, and T is going to be relatively small. But in principle, that for the moment is not going to matter. It's not the kind of small n, large p that I'm going to talk about. I will be focused on the other type of high dimensionality. Now, how do you model the kind of connections? Well, there's different ways we could go about doing things. Typically in genomics, people talk about motifs, and motifs basically means the way proteins activate genes and how they kickstart transcription into action. It could simply be by the fact that there may be a single protein, P2, that activates 3 genes below it, and this would simply called a single input motif in the center. It might be that there's a need for 2 proteins in order to activate a single transcription. That would be a multiple input motif, and it could be more complicated triangular kind of motifs that typically are called feed-forward loops. Could be negative, could be positive, etc. And so meaning of these arrows changes. Sometimes it's probably a binding of proteins. Sometimes it's actually a binding to a particular binding site on the gene, which allows the activation of this particular gene. So biological interpretation of arrows is changed quite a bit, depending on what you're actually talking about. Now this is lots of detail about a way of modeling it. This particular model is not the one that I'm going to use, but it's something that you might want to aim for. We've used it in a different context with slightly fewer genes, but it's something that you could do. If you want to do a kind of realistic modeling of kind of an average behavior of the activation of a set of genes, you typically want to think about an ordinary differential equation, a way of doing it. And an ordinary differential equation typically consists of two different bits. One is the decay bit over here. So basically it says, well, the changes in the transcription of a particular gene I at time t, well, that's due to the decay of a particular amount of these molecules present at that particular time of this gene I. Plus, there's some new genes, new gene I, or new RNA from gene I produced by some kind of transcription factor eta at time t, and that was the production term p it eta, basically. This is a rather general way of describing it. Now, for single input motifs, you can make it actually rather nicely explicit. For multiple input motifs, it becomes slightly more complicated. But all the parameters here have biological interpretations, and in a way it would be nice to be able to do this. For this particular talk, I will just focus on a slightly simpler type of kinetics, just a usual linear model, except that in the linear model we introduce basically our parameters, our x, this high-dimensional state, and this x stand for, again, whether or not there's a link present, yes or no. You can clearly see it's over-parameterized. There's no way in this sense of distinguishing between x and alpha. They're both parameters we need to estimate from the data, but we basically think of x, I, j as the things that we were interested in, whether or not there's a link present between gene I and gene j. So again, it's a model that tries to model the average amount of transcription of a particular gene at a particular time. Couple of observations. If people are familiar with the literature, it has some similarities with a partial correlation model. It's not really a model, but an algorithm to actually estimate some of the parameters. But we're not going to really think about our model in that way, because we would like to come up with, we would like to distinguish between all the parameters in our model, and particularly we'd like to come up with some estimates about xij, and we need to do so in a way that doesn't over-parameterize or overfit the data. We have typically very few data available in our model. So typical ways of doing it would be penalized inference and Bayesian inference with an informative prior. And again, we're not going to do something particularly dramatic about that, and so we need going to do some Bayesian inference with some prior. And we need to think about the prior that we want to use. Now, as you can think about, well, the parameters that we have in our model are these alpha ij's, which are going to be lots of them. There will be typically, well, there are n squared of them, where n is the number of genes, so typically very large. We have n squared xij's, again, quite large. And so we need to put up some kind of informative prior on our, in particular, our network, the xij's. And how can we do this? So I've already told you that these kind of networks, we have some prior idea about what we expect these networks to look like. The fact that they are going to be networks with a small world property, they have, in fact, certain amount of hubs present, makes it a type of model we can more or less a priori expect some form of the answer. We just don't know which ones are the hubs and which ones are the leaves of this particular network. But there is a nice so-called distribution made popular in physics in the last 15 years, so-called power law there, as they call it over there, and it basically gives us a marginal distribution on the or a distribution on the margins of our matrix X. So let's think about the margins of the matrix X. The margins of matrix X basically counts the number of links that each gene I has. And it simply says, well, we would like to have the number of links follow a particular distribution. So that's what we expect in advance. So it's a non-completely, so this particular distribution doesn't actually completely identify a full distribution on our axis. So it's only a partially informative prior that we're going to use. And typically, if you were to do full Bayesian inference, obviously that would be a problem because we still have not fully idea what x, the prior distribution of x looked like. But with what we're going to look at later on, it's actually enough in the inference that we're going to do. So the good thing about this power law is that indeed, if you were to simulate from these type of marginal distributions, you would get actually a network that typically seems to have the properties that these things like genomic networks and so-called internet websites have, this scale-free property. So again, as I said, so the constraint that we put in here is some kind of topological constraint that we put onto the topology of our network structure. There is kind of a hyperparameter necessary. This particular theta basically describes if theta is very close to 0, you will get a topology that is almost uniform. If theta is very large, you get one that actually is very spiky, so basically would have basically only a few with very many nodes, and basically majority having only 1 or 0 nodes. So this particular theta is not really a parameter in a kind of an usual sense. It is more like a tuning parameter in more traditional ways of looking at it. So we don't really want to estimate it very much from the actual data, because basically if you were to estimate from data, it would like to simply make it as small as possible. Well, that's just a detail in case you're interested. So now the issue that I'm going to talk about is basically how would you like to do inference in these kind of situations? And the kind of ideas that have come up in the recent past is things like approximate Bayesian computation, where you consider replacing the calculating the full density of the data by some density of some kind of summary statistic of the data, and basically all inference in that particular way. Now, that might work in some circumstances. In other circumstances, that could still be very hard to actually calculate. And our proposal is actually to replace the acceptance probability in general by an acceptance probability that involves some kind of a frequentist p-value in there, in which the p-value is associated with some test that captures some particular features of the distribution that you're interested in. In this case, if you look at the full algorithm in that case, so if you were to do some kind of inference in that particular way, you have some initial Markov chain with some particular x. You propose a new x. You calculate the associated p-value associated with this particular state, and you accept the proposal with this particular acceptance probability. And then you would return to 2. I think there's probably a bit of a likelihood missing over here, which was present over here. So this would be acceptance probability you would be considering. Now let's see how that works in some simple cases. So just the case of a normal mean. So you have data in this case, just drawn from a normal xi1. And clearly interested in this particular xi. I call it xi because it should refer to this parameter x that you are looking at, which now in that case obviously we know everything about the posterior distribution. In fact, posterior is going to look something like this quantity over here, and if you have some improper prior on x, you would get simply just something that looks like a normal with mean the average of your data, obviously, and a variance 1 over n. So that's would be a nice exercise for your first year students. And obviously, given that we actually have an explicit form of our solution, we could actually check what happens in case we were to apply the procedure I've just proposed. So in this case, you come up with your usual propose a new state. In this case, your test statistic that you would be using would simply be the usual t-test associated with the null hypothesis that x is equal to the current state of your Markov chain. So t statistic would be something like this one over here. And on the null, we know that this is t distributed with n-1 degrees of freedom. And we get a two-sided p-value equal to this particular t tail probability. And we would accept the proposal that we just made over here because it's symmetric in this particular way. And that would just be the ratio of p-values. So how does it work in practice? Well, we have the theoretical distribution over here, which I'm not sure if you can see it very well. It's this one over here. It has a little peak going slightly below the two peaks that you might see over here, and then kind of go down. And obviously this is just the normal, the explicit normal that we have derived. And what you find over here is that it looks indeed like that the MCMC, which is taken after 20,000 sweeps in this case, has properties almost identical to that of the explicit result. In fact, if n goes to infinity, it does look like you actually do completely exact inference. So it gives solutions that are close to exact inference in the case in which your test statistics is actually a sufficient statistics, and that's a nice property. So in this case, how we do this, on the example that I've just described to you, what would be the thing that we'll be looking at? Well, as I more or less shown you, the directed acyclic graph that I showed you is almost perfect for doing inference, except that we need to obviously update this x conditional on theta, sorry. And so what we do is we come up with a particular test statistic. Now remember that we have only specified in this case how the prior of x marginally. So we have no full knowledge, prior knowledge about x. But it's not really necessary. If we introduce the test statistic to be the goodness of fit statistic, that simply tests whether or not the current proposal of x is actually consistent with the power law with parameter theta, and then we have this particular usual goodness of fit chi-squared statistic, and we could simply calculate p-values, just a single value for your whole matrix X of the size n by n. That would just be a tail probability of a chi-square. So in this case we could do inference, obviously. Now if you were not to use any of the data, you basically would in the end up indeed sampling from a chi-square distribution. That's nice. You can show if you simply would ignore the data present, you would sample in the end from you would sample from a power law. Or at least the things that you draw would be consistent with the power law, which is nice, which probably is exactly the same thing. But obviously, given the fact that we have data, what does that mean? Well, it simply means that depending on how much data you have available, it would simply adjust this particular power law to satisfy and kind of suit the data that is there. So it kind of the data simply pulls the kind of final answer away from this particular power law. And clearly you would insert this particular additional term, the likelihood of the data as well. So we had an application in which we looked at a yeast subnetwork and with a small number of genes, basically about 25 genes in there. Tong et al. In 2004 published a way of coming up with some description of this particular network. And they used a type of technology that was quite different from microarrays. They looked at synthetic screen arrays, so completely unrelated to microarrays, and they come up with a way of describing for all these genes, about 25 in this particular subnetwork, whether or not there was a link present. So they basically had what we looked at as being the true adjacency matrix. And the true adjacency matrix, sorry, this was taken directly out of their paper in a rather crude manner, was this particular network over here, and the central gene in here that they found was one that this was in yeast, but it was one that had similarities with the Blumen-Werner syndrome genes. So what we did was basically for the data that we had available, I should say, see that I haven't described the the data we have, we had about a time course of about 77 microarrays available, and we basically said, okay, well, let's see what we can do effectively coming up using this particular method to do inference on this particular subnetwork. So the results. Well, the results that we're particularly interested in is basically looking at this adjacency matrix X effectively. And the adjacency matrix X basically has a set of connectivities, and so we, as you can see, at most can be 25. And it seems to have this particular properties of having indeed very few with many connections and many with few connections, the kind of thing that we expect from a network that is scale-free. And more importantly, if we were to compare the kind of the results that we get with the ones that Tong obtained, there's clearly differences. We predict several that are absent, that they say that are present, and vice versa. But the diagonal is quite large, and indeed, I mean, if you were to see, there's quite a significant overlap between these two methods. So it seems to be doing something sensible. Now, the fact that it does something sensible doesn't really rely on the fact of the algorithm that I've just proposed, but it's so because basically, if you had done, and you could have done, certainly in this case, full Bayesian inference, you would have obviously gotten something similar. So one thing that I've discussed over here, basically, I've tried to introduce a sampler that is useful for high-dimensional states, especially if you have to calculate things that are in a large order away from quantities in which n is basically extremely large. Also can be very useful for if you want to specify your prior for the quantities that you're interested in, particularly when you have these high-dimensional states. Coming up with a full prior is typically not very sensible. You might be able to say something about some of the summary statistics of this particular high-dimensional state, but it's very difficult to come up with a full specification, prior specification of the full high-dimensional state. But then again, this particular type of sampling is quite able to deal with that, because it basically will anyway look at the summary statistics that only focuses on these type of summary statistics. So in those two cases, we have looked at a new way of doing MCMC sampling, which can be quite useful in things like genomic applications. In case the summary statistic, the test statistic you use, is actually sufficient for the parameters that you're interested in. So if your summary statistics is sufficient for X with respect to the parameters, then you get inference that is at least close to exact. And finally, in case of in this particular experimental case, we looked and we found a nice overlap between prediction of a network by a kind of a genomic method and this particular statistical method just based on microarray data. So I know I have more time available, but I wanted to leave it right over here. Thank you very much.
Well, this is great. We've got loads of time for discussion and questions. Yeah.
Yes.
Very interesting. So bullet 2 is clearly false. I mean, I can imagine it being exact in some discrete spaces.
Mm-hmm.
But to make it closer to true generally, you would want the density of the sufficient statistic, the density ratio rather than the ratio of tail errors.
That's true, yes,
Which
exactly.
leads to the question, you've got a new MCMC sample, okay, so it's a Markov chain.
Uh-huh.
What does it converge to?
Uh-huh. That's a good question. So basically, it's true that basically what you're looking at is the, I mean, for this very simple case, in fact, the one that we looked at, the tail ratios are not even, I mean, even there, they're not the same as the density ratios. So there is simply, they're not completely overlapping. They will overlap to they will basically converge to something that might be interesting. But just as in approximate Bayesian computation, we don't quite know what it converges to, except in a few special cases. Yeah.
But you can write down mathematics.
Oh yes.
Figure out exactly what it converges to
Yes.
theoretically in certain examples.
For certain examples you can, and in fact for the the normal case, we have several explicit formulations. Yes.
Yeah, Matthias? Yeah. can you prove there's one stationary distribution of this? I mean, must not be the posterior of something, but is there at least one, or could it just cycle between lots of them?
No, it tend to have one. Well, okay. So there are in the case of the ones that the application that we looked at, there it's likely there are more stationary points. In the special cases that the special case that I dealt with in the very beginning, it will converge to a single stationary distribution, and you can actually write it down. But for the underspecified, as soon as you start to underspecify your priors, it will probably have several stationary distributions that it might converge to.
Would it be fair to say that actually this p-value is just a kind of modified prior in some sense, or? So if you just use a standard MCMC, that p-value is just replacing what would be known as the prior, isn't it?
No, it won't replace the prior. It replaces because basically no, it doesn't replace prior. It replaces effectively the ratio, the probability of x given your hyperparameters, which
if I was just to use standard MCMC, I have exactly the same formula, where I would have the prior in the place where you have the p-value. Isn't that true?
I think you're right. I'm just trying to. But I just don't. Okay, I'm struggling there. Sorry. Yes.
That's okay. Actually, I had a slightly related question, which was that I guess a lot of these genetic guys, they like sparsity, right? They like, maybe it's not just the degree distribution which is of interest, but also the connectivity structure is weak, it's sparse.
Right.
I don't see any component or ingredient like that in your framework, actually. So how do you justify this to the biologists?
Well, you could. I mean, the kind of price you put into, you could put additional constraints in. All this did basically was putting a kind of a topological constraint on the number of connections, not so much on the structure of the connection. So you could, for instance, kind of claim that you would like to have the connection somewhere on a particular diagonal through your network, which would basically have kind of sparsely connected substructures. So you would have to come up with a particular prior distribution that actually tries to capture that and effectively. I certainly wouldn't know on the top of my head how to do it, but.
Well, I guess we saw some earlier, right? There is this idea if you can look at latent variable structures.
Oh yes. In fact, yes, indeed, I made some note of that, and I think yes, that's trying to look at some kind of hyperspace in which you want to put them close together might be a way of doing it. Yeah.
Yes,
I may miss something. So when you're finding p-value for px given theta, are you using the data y to find it out?
No. It depends on which one you mean, which example you mean. So basically, in the case of the last example that I showed you, basically it's the x is just based on the current state of your network structure, so your adjacency matrix, and so the data y doesn't enter into the calculation of this p-value.
There's something I find funny about what you're doing in the following sense. To me, your p-value is a statistic that's it's a pivot. That is, it can have mean zero and so forth. Whether you call it a z or a p, whatever transformation, based on what you've assumed about the marginal distribution of the number of the distribution of the number of arrows going out of each guy, and you're using that. I can't sit here and figure out what your algorithm's going to do, but even if your algorithm was great, I have a feeling it'll depend on your your proposal. I think what's going to happen is everything's going to depend on your proposal distribution. Because your proposal distribution has to do with the joint distribution of the x's. But the only information you're using from the data is this particular marginal.
Yes.
So to me, first, intuitively, either you can have an identification problem about the joint, and it's going to depend what you pick as a joint, or perhaps what's worse is you have a small enough parametric model that you're going to determine the joint distribution of all these x's based on some restrictions you've put on the marginal, which is, these are the classic examples where people assume something's normal. They only see the left half of the data. Let's say it's censored at 0. And so all the inference is from the parametric model, about the right half of the data. You're you're extrapolating much more than anybody would do with a usual parametric model, because you have this idea, the marginals are given way, and you're using that little bit of information to tell you about the topology.
Oh, well, it's
Who's
true.
connected to who. And it just seems like not a good idea.
But you do want to put a very strong prior on your network structure. In this case.
Right, but you could imagine as a model,
Uh-huh.
again, that's right, that I put a strong prior on that, but I have the rest of the model parameterized, so that doesn't determine the joint distribution of the data. The joint distribution, other than the prior, is undetermined, and so you have to add more information if you want to infer something about the joint distribution. If you get identification, it seems to me you're getting it from having some connection between the marginal and the joint that you're not using any data information about at all, because the only data information you're using, in other words, the p-value ratio, you can see it as an approximation to the likelihood ratio. It's first order asymptotic. If you have a pivot and you do the asymptotic expansion, you actually get the z ratio as the likelihood ratio, in a sense. But the only parameter it's telling you about is a parameter of the margins.
Yes.
Right, and that you're inferring everything from that. That's all.
Okay.
Seems a lot of extrapolation if it's identified.
Right. Well, I think the extrapolation bit I'm not too worried about. Because that's what the kind of information you'd like to put into the model. And the fact that.
Well, I guess that you'd have a certain marginal distribution of connections, fine, but why would that tell me so much about who's connected to who? Which is what you're really trying to get out of this. That's what's.
Well, it doesn't tell who's connected to who. It simply tells you that it doesn't force particular. The information of who's connected to who comes from the likelihood that you do use in the acceptance probabilities.
I thought the likelihood you're replacing it just by this marginal.
No, over here. So basically, had you just used this, you would indeed just converge to something that would just be completely.
Oh, okay.
So this is the one that you would use for inference. So you actually use your data y to inform you about who's connected to who. It's just that the marginal is the one that you want to have converged to.
Okay, maybe you're right, and I misunderstood. I take it all
Well,
back.
I'm not sure if
I may take it all back.
But
I didn't
I think
understand what you were-
there is a connection in the sense that
Well,
if you were to have a stronger prior, which wasn't just upon the degree of distribution, perhaps you would need less of the likelihood term to actually get you good inference or to identify the parameters as well. I think
Right,
that's
if you
the
want
way
to
of these
identify the parameters based
mixing
on the
these.
margin.
Yeah.
But the posterior is usually a density, and then a p-value is usually a tail probability when somebody's integrated the density.
yes.
So it seems strange to substitute. Like a tail probability might have an infinite integral, and so then there wouldn't be a stationary distribution. Could you sort that out?
Well, I think there are cases in which there may be simply no stationary distribution. That might well be.
Well, like a one-tail p-value.
Uh-huh.
Take half the space would have probability above like 5.
Right. Okay, so I think in the cases that I think in the case of, in this particular case, there may be, I think there might be several stationary distribution, but I'm not sure if there's actually, are you worried about the fact there may be actually none at all?
I think if well, not for your p-value, you'd have to actually deliberately pick a bad one.
Uh-huh.
A one-tailed p-value
Right.
probably would.
Okay.
Have that trouble.
Yes. You might be right there, yes.
Any more questions? Okay, let's thank Ernst again.